I'm glad to say thanks all the organizing committee. My name is Arebu Dejen. I would like to present my paper entitled Optimization of Dual-Band Microstrip Millimeter Wave Antenna with Improved Directivity for Mobile Application using Genetic Algorithm. I have organized my presentation in this fashion. First, we will see the introductory part. Next, we will see the antenna configuration and optimization part. Lastly, we will see the result and the analysis. So, since this paper is focused on millimeter wave frequency, let's start my presentation by asking a simple question: why it focuses on millimeter wave frequency? As everyone guesses, a massive growth of wireless data and the demand of high data rate. Beside this, with a bandwidth-hungry services like online gaming and video live streaming, the current microwave spectrum faces in bandwidth scarcity. So, ITU recommended that there are plenty of bandwidth available in millimeter wave frequency. Several researchers are working on millimeter wave frequencies. So, what are millimeter wave frequencies? Millimeter wave frequency is nothing but a frequency ranging from 30 GHz up to 300 GHz. However, a certain frequency less than 30 GHz behaves similar propagation characteristics like millimeter wave frequency, so that a newly defined 5G's new radio millimeter wave frequencies are ranging from 20 GHz up to 300 GHz. Some spectrum bands of millimeter wave frequencies have already identified for mobile communication, predicted like 24 GHz, 28, 31, 39, 47, and 50s are the predicted mobile communications for future millimeter wave communications. The other important question for this research is why dual band antenna is required. An increment of multiple service demand from a single mobile device requires an efficient multiband antenna technology, especially for the upcoming millimeter wave mobile communication. Multiband antennas are used to incorporate several communication standards in a single compact system. This attracts the researchers' attention. However, we know that antenna is a hardware device, so there are critical limitations existence in terms of exploring more operating bands. Even if we penetrate this critical limitation and create several operating bands, keeping high efficient in all the required bands also another challenge. So, investigation of a dual band or more band antenna with low profile is a current research area. So, several researchers are picking up microstrip patch antenna since it has several advantages because of its low volume, low cost, simple planar configuration, low weights, and easy to fabricate. However, the conventional microstrip patch antenna inherently has a narrow bandwidth, low efficiency, low gain, and less directivity. It is always a challenging task to develop a high directive and multiband microstrip patch antenna. So, why directivity improvement of antenna is necessary? Because since it is a key for overcoming some of the propagation challenges of millimeter wave spectrum, increase the spectral efficiency, and provides high data rate for mobile broadband services. There are several techniques to improve the directivities of patch antenna in the literature. Among them, a fractal shape geometry at 6, 7, and 8 reported, and frequency selective surface presented in 9 and 10 reference. Using a T transverse magnetic odd with zero mode is reported in reference number 11. Genetic algorithm optimization also presented in reference 12, 13, and 14. This paper presents a dual band patch antenna optimization using binary coded genetic algorithm for millimeter wave frequency with improved directivity using by the following methodologies. The proposed antenna was analyzed and modeled on HFSS software in combination with MATLAB. The genetic algorithm optimizer checks the fitness function continuously for every population until the end of the iteration or the termination criteria is reached. So this diagram will illustrate more about how to utilize both MATLAB and HFSS in to solve our problem. MATLAB software is utilized to generate a visual basic scripts that can be helpful or an input for HFSS software. So HFSS software calls the visual basic script files that are generated from MATLAB, and these visual basic script files have all the details of the modeled antenna. So HFSS software starts to model the antenna from Visual Basic script, and then try to compute, analyze, and export the result to the MATLAB again. So the genetic algorithm try to evaluate the cost function based on the result exported from HFSS. So this is optimization procedure for a single iteration basically. So next one is, what is genetic algorithm? We are talking about genetic algorithm. Genetic algorithm is based on the process of natural selection. It is a powerful, robust, stochastic-based optimization method in solving electromagnetic problems. Each individual in genetic algorithm is represented by a chromosome. The first generation is created by a random mechanism. The rest is created by a reproduction mechanism. This is the overall flow chart of genetic algorithm. The randomly initialized population is directly evaluates their cost function, and then after evaluation of their cost function, the operators will create the next generation by a crossover to create a new offspring. Mutation creates more diverse the population. Selection will ranking and picking up the next generation based on the cost function. So if the criteria is satisfied, the process will be terminated and return to the base. However, it will be back to evaluation of the cost function on each generation. Now let's see the antenna configurations. The proposed antenna is a rectangular microstrip patch antenna modeled in this figure as shown here. So it's modeled on Roger substrate with a thickness of 0.3 millimeter and dielectric constant of 2.2 on a finite ground plane with a size of 10.7 millimeter by 10.7 millimeter. As you see here, the size of the rectangular microstrip patch is 3.36 by 5.26 millimeter. So the rest of the dimension is summarized on this table. Basically, this antenna is not our actual antenna, it is our reference antenna needed to be optimized or an input for genetic optimization. So in order to optimize the patch geometry, or the patch surface is divided into 10 by 10 of the random and non-uniform small circular as shown in the figure. So as you see here, this one is only the patch surface, 3.36 by 5.26 dimension. It contains 10 circular cells in the vertical and 10 circular cells in the horizontal. The rest patch surface exists, and we are playing only on these cells. This cell contains two types of cell in dimension, small and large dimension, with a probability of 0.2 and 0.8 respectively. This helps us to create the varieties of circular geometry on the patch surface. So after having this, the next question is how to manage such cells to make a conducting and non-conducting. It can be done by a binary coding algorithm, basically. So if the cell is conducting, it can be assigned by 1. If the cell is not conducting, it can be assigned by 0. Our fitness function is designed based on maximizing the directivity and minimizing the reflection coefficient, or maximizing the negative of the reflection coefficient, and the required 2 bands only. So f, which is the frequency, the f, which is the fitness function, is equivalent to the summation of the directivity minus the reflection coefficient, where S11 is taken negative 10 dB if it is less than negative 10 dB. This helps us to protect the narrow boundaries of the proposed antenna. The general optimization setup is done by a population size is taken as 20 individuals. Each individual is represented by 100 generation, a single point crossover, 100 genes, a single point crossover with 70% probability used, a mutation rate of 0.02, and tournament selection mechanism have been applied. So the simulation is carried out until 150 generations. After 150 generations, the fittest individual is this one. As you see here, the port, the microstrip line, and the substrates are not changed. Our intention is optimizing the path geometry only, so that on the path geometry, there are a number of slots, circular slots are existing. So this geometry is obtained after 150 generations. This diagram shows that the fitness value versus generation, and the fitness value starts to be converged after 130 generations. After 130 generations. Now let's see the results of these outputs, or these fittest individuals. As you see here, the both proposed genetically engineered and reference patch antenna was simulated using HFSS software, and this diagram shows that the reflection coefficient plots, or S11 plot in dB versus frequency in gigahertz. A proposed antenna, which is assigned as by a pink color, it is only resonated at 28 gigahertz with a peak S11 of negative 17.9 dB, whereas the red one, which is genetically optimized antenna, can resonate at 2 frequencies. We can say that this as a dual band antenna, and at 28 gigahertz, and the same at 31.1 gigahertz. At 28 gigahertz, negative 12.1 a peak S11, and at approximately 2.9% bandwidth. At 31.1 gigahertz, a peak S11 of negative 12.3 dB, and approximately 1% of bandwidth is obtained. So our genetically optimized antenna is a dual band antenna. The other important parameter we are going to explain is about the directivity of the antenna. Basically, in conventional microstrip patch antennas have directivity not more than 7 dB. Accordingly, our reference antenna have 6.8 dB. But when you see this genetic algorithm optimized antenna, it has improved directivity at both 28 gigahertz and 31.1 gigahertz. Well, let's see at 28 gigahertz. At 28 gigahertz, the peak directivities of the antenna at phi is equals to 0, or at phi is equals to 90 degrees, with approximately similar beam widths. Their peak directivity is 8.6 dB. However, when you come come to here at 31.1 gigahertz, the genetically optimized antenna have a directivity of 10.9 dB with phi is equals to 90 degree is a little bit wider beam width. Phi is equals to 0 degree is a little bit narrow beam width relative to phi is equals to 90 degree. It has more side lobes and back lobes. Generally, the overall performance of genetically optimized antenna compared to reference antenna is summarized in this table. Now let's see the current distribution of both reference antenna and the genetically optimized antenna at their resonant frequency. Now let's see, for instance, when you see the reference antenna, the current distribution of reference antenna, it can be peak current distribution at the edge of the patch. Whereas when we come to genetically optimized antenna, it can have a peak or high current distribution at both the edge of the patch at the same at the edge of the cells at 28 gigahertz. When you come to here at 31.1 gigahertz, it's almost at the edge of the cells and the edge of the patch. So the presence of this circular slots at the patch surface will help to create additional resonancy at the same to improve the directivity. This paper, as a conclusion, this paper presents a dual band directivity improvement using genetic algorithm optimization, and the proposed genetically optimized antenna was simulated in HFSS and compared to the reference antenna. The result explores that the optimized antenna is operated in two resonant bands at 28 gigahertz with bandwidth of 2.9% and at 31.1 gigahertz with a bandwidth of approximately 1%. The directivity of the proposed antenna is improved to 8.6 dB and to 10.9 dB respectively. When you compare it to 6.8 dB of reference antenna. So this antenna the proposed antenna is advantageous for millimeter wave mobile communication. These are some of my references, and thank you for listening to my presentation.